Before you open this case file, I have a challenge for you. Stay with me until every piece of evidence has been examined. Because by the end of this investigation, you will be asked a simple question. If you had been responsible for protecting one of the fastest growing technology companies on Earth, would you have seen the warning signs before disaster struck? Every major cyber attack leaves behind a trail. Sometimes it's hidden inside firewall logs. Sometimes it's buried in lines of source code. Sometimes it's found in forgotten credentials, overlooked alerts, or decisions made under pressure. The Uber breach left behind all of those. But unlike many famous cyber attacks, this case wasn't defined solely by how the attackers broke in. It became one of the most controversial cybersecurity incidents in history because of what happened after the intrusion was discovered. To understand why, we must first understand the company at the center of the investigation. The year was 2016. Only a few years earlier, calling a taxi often meant standing on a street corner, waving at passing vehicles, or waiting on hold with a dispatcher who could only estimate when a driver might arrive. Transportation had changed very little for decades. Then came Uber. With a few taps on a smartphone, anyone could request a ride almost instantly. The application automatically calculated the fare, displayed the driver's location in real time, processed payment without cash, and recorded every trip inside a digital account. For customers, it felt effortless. For software engineers, it was an extraordinary technological achievement. Behind that simple interface operated one of the largest cloud-based platforms in the world. Millions of people opened the application every day. Every request triggered dozens of back-end services. Location services identified the rider. Matching algorithms searched for nearby drivers. Traffic systems calculated optimal routes. Pricing engines adjusted fares based on demand. Payment systems communicated with financial institutions. Notification services updated riders and drivers simultaneously. Every ride involved thousands of individual software operations occurring in only a few seconds. Most users never considered what made that possible. They simply saw a car arriving. Behind the scenes, however, Uber had become an enormous digital ecosystem. Thousands of servers, countless databases, application programming interfaces, cloud storage, microservices, developer environments, authentication systems, machine learning models, monitoring platforms, internal administration tools. Each component depended on another. Together they formed one of the most sophisticated technology infrastructures of its time. Growth came at an astonishing pace. New cities were added almost every week. Engineering teams expanded rapidly. New developers joined the company. New software features were released continuously. Innovation became part of the company's identity. In Silicon Valley, speed was everything. Launching new products before competitors often meant the difference between becoming an industry leader and becoming irrelevant. But speed has a cost. As organizations grow faster, their technology grows more complex. New employees require access to development systems. New projects require cloud resources. Developers share code through collaborative platforms. Automation becomes essential. Secrets such as passwords, authentication tokens, and access keys begin flowing through countless development pipelines. Managing those secrets becomes increasingly difficult. Cybersecurity professionals understand an important principle. Every organization has an attack surface. An attack surface is every possible point through which an attacker might gain unauthorized access. Public websites, employee laptops, mobile applications, cloud infrastructure, remote access portals, programming interfaces, third-party vendors, development repositories. Every new system increases opportunity, not only for innovation, but also for attackers. By 2016, Uber's attack surface had expanded dramatically. The company operated in hundreds of cities across the globe. Millions of users trusted the platform with sensitive information. Customers shared their names, email addresses, telephone numbers, payment information, trip histories, pickup locations, drop-off locations, travel habits. Meanwhile, drivers entrusted Uber with even more. Government-issued identification, driver's license information, vehicle registration documents, insurance records, banking details, employment records, background check information. Each new customer increased the value of Uber's databases. Each new driver increased the amount of sensitive information stored inside company systems. Data became one of Uber's most valuable assets. It also became one of its greatest responsibilities. Every successful cybercriminal asks the same question: where is the most valuable information? The answer often determines the target. Banks hold financial records. Hospitals store medical histories. Governments maintain citizen information. Technology companies collect behavioral data on an enormous scale. Uber possessed all of these in different forms, not because it intended to become a repository of sensitive information, but because modern digital services naturally accumulate data over time. Every completed ride left another permanent record. Every updated account added another piece of information. Every support request generated additional documentation. Every software deployment created new infrastructure. Every engineer received another set of permissions. From a cybersecurity perspective, growth was creating something else: complexity. Complexity is one of the greatest enemies of security. The more systems an organization operates, the harder those systems become to monitor. The more employees have privileged access, the more difficult access control becomes. The more software repositories exist, the easier it becomes for one mistake to remain unnoticed. History has repeatedly demonstrated that attackers rarely succeed because organizations lack sophisticated technology. Instead, they succeed because ordinary mistakes become invisible inside extraordinarily complex environments. One forgotten server, one outdated application, one excessive permission, one exposed credential, one overlooked repository. Those seemingly insignificant details have changed history more than once. Long before investigators reconstructed the Uber breach, those mistakes already existed. They simply hadn't been discovered yet. Somewhere inside Uber's development ecosystem, a small decision had already planted the seed for one of the most controversial cybersecurity investigations ever conducted. No alarm sounded, no malware executed, no firewall detected an intrusion. Employees continued writing software. Executives continued expanding the business. Customers continued requesting rides. Drivers continued earning income. Everything appeared perfectly normal. But appearances can be deceptive, because somewhere beyond Uber's offices, someone was already searching, not for Uber specifically, but for companies that had unknowingly left a door unlocked. The investigation had already begun. Neither Uber, nor its millions of users, knew it yet. Every cyber attack begins long before the first unauthorized login, long before data is stolen, long before investigators arrive, long before headlines appear across the world. Professional attackers rarely begin by attacking their target directly. Instead, they begin by asking questions. What technologies does the company use? Where do employees collaborate? Which cloud providers host its infrastructure? What programming languages are its developers using? What information has been exposed accidentally? Every answer narrows the search. Every clue reveals another possible path. This phase is known as reconnaissance. Military strategists have practiced it for centuries. Modern cybercriminals simply perform it through the internet. Rather than observing buildings through binoculars, they observe digital footprints, public websites, DNS records, certificate transparency logs, open source intelligence, social media, technical documentation, software repositories, job postings. Every organization unintentionally reveals information about itself. Recruitment advertisements mention programming languages. Developer blogs discuss architecture. Conference presentations explain engineering practices. GitHub profiles reveal coding activity. Cloud services expose metadata. None of these pieces seem dangerous on their own. Together, they create a remarkably detailed picture. Investigators later concluded that the attackers targeting Uber demonstrated patience. There is no evidence that they immediately launched sophisticated exploits against Uber's infrastructure. Instead, they searched for opportunities that already existed. Like experienced burglars walking through a neighborhood, they weren't looking for the strongest house. They were looking for the one with an unlocked window. Modern software development depends heavily on collaboration. Large engineering teams cannot simply exchange source code through email. They rely on specialized platforms that track every modification, every bug fix, every software release, every contribution. One of the most widely used platforms for that purpose was GitHub. GitHub transformed software development. Developers from around the world could collaborate on projects regardless of location. Teams could review code before deployment, track issues, manage releases, maintain version histories, The platform became an essential part of modern software engineering. Like countless technology companies, Uber relied on GitHub during its rapid expansion. Thousands of software changes occurred constantly. Engineers worked on different services simultaneously. Microservices evolved independently. Continuous integration pipelines automatically tested new code. Automation accelerated development. The benefits were enormous. But every collaboration platform introduces responsibility. Not every repository is intended for public viewing. Many organizations maintain private repositories containing proprietary source code. Those repositories often include configuration files, deployment scripts, infrastructure templates, internal documentation. Sometimes, developers also include information that should never appear in source code. Passwords, access tokens, API keys, cloud credentials. Security professionals refer to these as secrets. Secrets are exactly what their name implies. They provide trusted access to protected resources. Applications need them. Automation systems need them. Deployment pipelines need them. But they must remain confidential. Embedding secrets directly into source code is considered one of the most dangerous mistakes in modern software development. Unfortunately, it also happens more often than many organizations realize. Imagine writing the master key to a bank vault inside the bank's employee handbook. Even if only employees can read that handbook, the risk still exists. If anyone unauthorized gains access, they immediately possess the key. Digital credentials function in much the same way. Investigators later determined that Uber's attackers discovered credentials stored inside a private GitHub repository. Those credentials provided access to Amazon Web Services, better known simply as AWS. To understand why this mattered, we need to understand cloud computing. Traditional companies once operated physical servers inside their own buildings. Entire rooms filled with hardware, cooling systems, network equipment, backup power, storage arrays. Managing those environments required enormous investments. Cloud computing changed that model. Instead of purchasing physical servers, organizations rent computing resources from providers such as Amazon Web Services. Need another database? Create one in minutes. Need additional storage? Allocate it instantly. Need hundreds of virtual servers? Deploy them automatically. The cloud dramatically accelerated innovation. But it also introduced a new reality. Access to enormous infrastructure could now depend on a single credential. Possessing valid cloud credentials can be far more valuable than exploiting a software vulnerability. Attackers no longer need to force their way inside. The system recognizes them as authorized users. From many security tools' perspective, nothing appears unusual. This distinction is critical. Hollywood often portrays hackers defeating impossible encryption through extraordinary technical skill. Real-world investigations frequently reveal something different. The attackers simply logged in, using credentials that should never have been exposed. According to investigative findings, the credentials recovered from the GitHub repository enabled access to Uber's AWS environment. At first glance, this might not sound catastrophic. Cloud environments contain thousands of different resources. Not every credential grants unrestricted access. Permissions determine what each identity can do. Security professionals call this identity and access management, or IAM. IAM follows an important principle. Every identity should receive only the permissions necessary to perform its task. Nothing more. This concept is known as the principle of least privilege. If a developer only needs access to one application, they should not automatically gain access to customer databases. If an automated deployment system only uploads software, it should not possess administrative control over cloud storage. Least privilege limits damage, even when credentials are compromised. But implementing least privilege across rapidly growing organizations is difficult. Permissions accumulate over time. Temporary access becomes permanent. Projects evolve. Employees change roles. New cloud resources appear daily. Without careful governance, permissions expand quietly. Investigators examined whether the compromised credentials provided broader access than necessary. The answer would prove significant. Once inside Uber's cloud environment, the attackers began exploring. Not recklessly, methodically. Professional intruders understand that immediate action attracts attention. Instead, they observe. They identify storage locations, review cloud resources, map relationships between systems, learn naming conventions. Discover administrative accounts. Search for backups. Locate databases. Each discovery answers another question. Each answer points towards something more valuable. This process is remarkably similar to an investigator walking through a crime scene. Every hallway, every locked cabinet, every office, every document. Gradually, a complete picture emerges. Inside cloud environments, attackers perform that same process digitally. They enumerate storage buckets, inspect permissions, review configuration files, search metadata, identify service accounts, locate snapshots, examine deployment histories. Every action increases understanding. Every minute spent learning the environment improves the likelihood of success. Throughout this entire process, Uber's customers noticed nothing. Drivers noticed nothing. Executives noticed nothing. Millions of rides continued without interruption. Applications functioned normally. Payments processed successfully. Maps updated correctly. The company's enormous infrastructure continued operating exactly as designed. Because from the outside, nothing had changed. Yet somewhere inside Uber's cloud environment, individuals with unauthorized access were quietly learning how the company's digital world operated. The compromise had not yet reached its most damaging stage. The attackers had found the doorway. Now they were searching for the vault. The next phase of the investigation would reveal what they ultimately discovered, and why tens of millions of people would eventually become victims of one of the most controversial breaches in corporate history. The most dangerous moment in a cyber attack is rarely the initial compromise. It's what happens after. Breaking into a system is only the beginning. Remaining undetected, that is where professional attackers separate themselves from amateurs. When investigators later reconstructed the Uber breach, they found no evidence of attackers recklessly downloading every file they could find the moment they gained access. Instead, the activity suggested patience, discipline, planning. The unauthorized users behaved less like burglars, and more like explorers entering unfamiliar territory. Imagine walking into an enormous library in complete darkness. You don't immediately begin taking books. First, you learn the layout. Where are the entrances? Where are the exits? Which rooms contain the rare collections? Where are the security cameras? Which doors require special keys? Only after understanding the environment do you decide what is worth taking. That same philosophy applies to modern cyber intrusions. Inside Uber's cloud infrastructure, the attackers first needed to understand what they had accessed. Cloud environments can contain thousands of different resources: virtual machines, storage buckets, databases, application service, identity services, monitoring tools, encryption keys, development environments, testing platforms, backup systems. Every organization structures these resources differently. Without a map, even attackers with valid credentials can become lost. Investigators believe the intruders spent valuable time studying Uber's cloud architecture before attempting to access sensitive information. This phase is known as internal reconnaissance. Unlike external reconnaissance, which relies on publicly available information, internal reconnaissance begins after unauthorized access has already been achieved. The objective changes. Instead of asking, "How do we get inside?" the question becomes, "What have we just entered?" Attackers begin collecting information: cloud account names, project identifiers, security groups, identity permissions, database locations, administrative accounts, network relationships. Every discovery increases their understanding of the environment. Cloud providers record much of this activity automatically. Every login, every API request, every permission check, every attempt to list resources. Each action leaves behind evidence. Digital footprints. Unlike physical footprints, however, cloud logs often contain millions of legitimate events every day. Separating malicious behavior from normal administrative activity can become extraordinarily difficult. Imagine trying to identify one unfamiliar face in a city of millions. The face exists, the evidence exists, but recognizing it requires attention, context, and effective monitoring. Large organizations generate staggering amounts of telemetry, application logs, authentication events, infrastructure metrics, container activity, network flows, storage requests, identity changes. Every second, every minute, every hour. Security operations centers, commonly known as SOCs, exist to monitor these environments. Their mission is simple in theory: Detect suspicious behavior before attackers accomplish their objective. In practice, the mission is anything but simple. Security analysts receive thousands of alerts every day. Some represent genuine attacks. Others are harmless anomalies. Still others are false positives triggered by legitimate business activity. Determining which alert deserves immediate attention requires both experience and context. Professional attackers understand this reality. Rather than generating obvious warning signs, they attempt to blend into ordinary operations. If administrators routinely access cloud storage, attackers use cloud storage. If engineers frequently retrieve backups, attackers retrieve backups. If automated systems authenticate every few minutes, attackers mimic automated behavior. The goal is invisibility, not by becoming invisible, but by becoming ordinary. One of the most effective techniques in modern cyber operations is known as living off the land. Instead of introducing malicious software, attackers rely on legitimate administrative tools already present within the environment. No custom malware, no suspicious executables, no destructive payloads. Only authorized commands executed by unauthorized people. This strategy significantly complicates investigations. Security tools often focus on detecting malicious software, but when attackers use legitimate cloud management interfaces, the activity can resemble everyday administration. The difference lies in intent. An intent is much harder to detect than software. Inside Uber's AWS environment, the attackers continued expanding their understanding. Cloud storage became a logical destination. Modern cloud platforms often separate compute resources from stored information. Applications perform calculations. Storage services preserve data. Databases organize records. Together they support the services customers use every day. Uber generated extraordinary amounts of information. Every completed trip produced records. Every account update modified databases. Every customer interaction generated metadata. Every driver onboarding process created documentation. Millions of users, millions of rides, millions of transactions. The company's infrastructure reflected that scale. Investigators would later determine that the attackers eventually located repositories containing personally identifiable information. Cybersecurity professionals frequently abbreviate this as PII. Personally identifiable information includes data capable of identifying a specific individual. Names, email addresses, telephone numbers, physical addresses, government-issued identification, license numbers, date of birth. Individually, some of these details may appear harmless. Combined, they become remarkably valuable. Identity thieves rarely depend upon one single piece of information. Instead, they assemble complete profiles. Every additional data point increases confidence that an identity can be impersonated successfully. Criminal marketplaces assign value accordingly. A simple email address may have limited worth. An email address combined with a verified telephone number becomes more useful. Add a government-issued identification number, and the value increases dramatically. Add financial information. The profile becomes even more attractive. This is why attackers often seek complete datasets rather than isolated records. The Uber breach primarily exposed names, email addresses, telephone numbers, and driver-related information. Although payment card numbers were not among the principal datasets reported, the exposed information still represented significant privacy risks, particularly for professional drivers. Approximately 600,000 US drivers had driver's license numbers exposed. At first glance, that figure appears much smaller than 57 million. But cybersecurity investigations rarely focus only on quantity. Impact matters. A driver's license is more than an identification card. It verifies identity, supports employment, confirms legal authorization to operate vehicles, can assist in identity verification for numerous services. Replacing compromised identification documents often requires time, expense, and administrative effort. For affected drivers, the breach carried consequences extending well beyond inconvenience. Meanwhile, the attackers had accomplished their primary objective. They had located valuable information. The final stage remained: removing that information from Uber's environment without attracting immediate attention. Data theft inside cloud environments differs from stealing physical documents. Digital information can be copied without removing the original. The victim often continues using the data normally. Nothing appears missing. Databases remain intact. Applications continue functioning. Customers continue logging in. The original information still exists. Only now, someone else possesses a copy. This characteristic makes data breaches uniquely dangerous. Organizations may remain unaware for weeks, months, or even years. The attackers understand this, which is why exfiltration, the transfer of stolen information outside the victim's environment, is often performed carefully. Large transfers attract attention. Smaller transfers spread over time can blend into normal network activity. Investigators studying sophisticated intrusions frequently compare exfiltration to slowly removing water from a lake using a cup instead of a bucket. The change becomes far less noticeable. Exactly how every stage unfolded inside Uber's cloud environment remains known only to those directly involved. But investigative findings confirm the outcome. Approximately 57 million user and driver records have been accessed. One of the world's fastest-growing technology companies had suffered a major compromise. Yet remarkably, almost nobody outside a small group within the company knew. Customers continued requesting rides. Drivers continued earning income. Investors continued watching the company's extraordinary growth. From the outside, Uber appeared unstoppable. Inside, a decision was approaching that would define the case forever. The technical breach had reached its conclusion. The ethical crisis was only beginning.